This is stochastic processes, Module 8 renewal processes. In the lecture 1, we have discussed the renewal function and renewal equation. In the lecture 2, we have discussed generalized renewal processes and renewal limit theorems. In lecture 3, we have covered Markov renewal and regenerative processes. In lecture 4, we have discussed non-Markovian queues such as MG1Q, MG1NQ, MGCC, loss systems. This is lecture 5, non-Markovian queues. In this lecture, we are going to discuss GIM1Q, GIMCQ, then GIM1NQ, and finally GIG1Q. What is GIM1Q? It means the inter-arrival time follows a non-exponential distribution which are independent. Therefore, the GI, some books they use only G as a notation. M stands for the service time is exponential distribution. Only one server in the system with the infinite capacity. So consider the customers arrive at a time points at T0, T1, T2 and so on. Let Zn is equal to Tn plus 1 minus Tn be the IID random variables with the distribution function with the CD of A with the mean 1 by lambda. Therefore, as a special case, if you assume that the inter-arrival time is a exponential distribution with the mean 1 by lambda, then the arrival follows a Poisson process with the parameter lambda. But in this GM1 model, the inter-arrival time is a non-exponential distribution with the CD of function A with the mean 1 by lambda. Let the service time distribution be exponential with the mean 1 by mu. Let Q2 be the number of customers in the system at time t. So Qt for t greater than or equal to 0 is a stochastic process. Since the Qt is a number of customers in the system at any time t, therefore the corresponding stochastic process is a discrete state continuous time stochastic process. So the underlying stochastic process in the GM1Q is a Qt t greater than or equal to 0. Now define Q of t n minus 0 as a Qn. Thus, Qn is the number of customers in the system just before the nth arrival. Qn is the number of customers in the system just before the nth arrival. Therefore, the Qn for n is equal to 1, 2 and so on, this follows a discrete state, discrete time stochastic process. So this is a embedded stochastic process from Q of t. The Q of t is a discrete state continuous time stochastic process, whereas the Q of n is a discrete state discrete time stochastic process, because the Qn is the number of customers in the system just before the nth arrival. The bivariate random variables Qn, Tn for different values of n forms a Markov renewal process, where Tn is the instant when the nth customers arrives and Qn is defined Q of Tn minus 0. Since inter-arrival time is a non-exponential distribution with the mean 1 by lambda and the service time is exponential distribution with the mean 1 by mu, single server in the system and infinite capacity. Therefore, the Qn comma Tn form a Markov renewal process, and the Tn is a time instant in which the arrival occurs. Now define the random variable xn as the number of potential service completions during the inter-arrival period Zn. Zn is nothing but Tn plus 1 minus Tn, that is the inter-arrival time. Xn is the number of potential service completions during the inter-arrival period Zn, and Pj be the distribution of Xn. Obviously, Xn is the discrete type random variable for fixed n, and the Pj is the probability mass function for the random variable Xn. Since the number of potential service completion could be 0, 1 and so on, so the probability mass function for different values of j, Pj's is nothing but the probability of Xn is equal to j, that is nothing but the integration 0 to infinity e power minus mu t power j divided by j factorial, and the integration with respect to a of t, where a of t is the distribution function of inter-arrival time with the mean 1 by lambda, and mu is the parameter for exponential distribution of service time. The way we define the Qn is nothing but the number of customers in the system just before the nth arrival. One can relate the Qn plus 1 in terms of Qn. We can find the relationship between Qn and Qn plus 1. That is, Qn plus 1 will be Qn plus 1 minus Xn plus 1. Whenever Qn plus 1 minus Xn plus 1 is greater than 0. Otherwise, it is 0 for Qn plus 1 minus Xn plus 1 is less than 0. The reason is the number of customers in the system just before the nth arrival, n plus 1th arrival, is same as the number of customers in the system just before the nth arrival plus the n plus 1th customer who arrived, that is plus 1, minus how many customers are served during the inter-arrival period, that is xn plus 1. So, if you subtract Qn plus 1, the xn plus 1, you will get Qn plus 1, whenever Qn plus 1 minus xn plus 1 is greater than 0. If it is less than or equal to 0, then the number of customers will be again 0. Just before the n plus 1th arrival also will be 0. We know that the xn plus 1 is independent of Qn plus 1. Hence, the Qn plus 1 depends only on Qn, and Qn plus 1 is independent of xn plus 1. Therefore, the Qn forms a time homogeneous discrete time Markov chain. The Qt is a discrete state continuous time stochastic process, and the Qn is the discrete time discrete state stochastic process. Since Qn plus 1 is equal to Qn plus 1 minus xn plus 1 or 0, and Qn plus 1 is independent of xn plus 1, as well as Qn plus 1 depends only on Qn. Therefore, the Qn for n is equal to 0, 1, 2 and so on form a time homogeneous means time invariant, and also it satisfies the Markov property. Therefore, this discrete time discrete state stochastic process is called a discrete time Markov chain, satisfying the time homogeneous property. Therefore, it is called the time homogeneous discrete time Markov chain. Once we know that Qn is a discrete time Markov chain, we can find the one-step transition probability matrix whose elements are Pij's. So, the Pij are nothing but what is the probability that Qn plus 1 will be j given that Qn was I. That is same as what is the probability that I plus j minus 1 customers are served during the inter-arrival time period. That is a probability of xn plus 1 is equal to I minus j plus 1 whenever j is greater than 0. If j is equal to 0, then it is nothing but a probability that xn plus 1 is equal to I plus 1. In matrix form, you can write it P as the matrix whose elements are Pij. So, the first element will be P1 plus P2 and so on, and the second element in the first row will be B0, B0. Since Pj's are nothing but the probability mass function for the random variable xn, that is for all n. For all n, it is identically distributed. Therefore, the probability mass function of xn is Pj's, and the running index for j is 0, 1 and so on. Therefore, if you make the row sum B0 plus B1 plus B2 and so on, that will be 1. Whereas in the second row, the first element will be B2 plus B3 and so on. The second row, second element will be B1, second row, third element will be B0 and so on. Substitute I and j in the above equation. If you substitute I and j accordingly, you will get these values summation of b's starting from 2 and b1, b0 and so on. Similarly, you can get the third row. You can verify that each element of a B, capital B matrix will be lies between 0 to 1 and the row sum will be 1. It's basically a stochastic matrix. This is a one-step transition probability matrix, capital P. Our interest is to find out the steady state or limiting distribution. For that, we need a irreducible and positive recurrent and aperiodic also. So, for the irreducible, you need B0 has to be greater than 0 as well as P0 plus P1 has to be less than 1. If this is satisfied, then you will get the conclusion the given time homogeneous discrete time Markov chain will be irreducible. That means each state is communicating with each other states with the condition of B0 is greater than 0, B0 plus B1 is less than 1. We can easily determine that the DTMs is aperiodic. We have discussed the aperiodic in the discrete time Markov chain. So, we can verify that this discrete time Markov chain is aperiodic also. That means with the period 1. Now, we find out the Laplace transform of the CDF of inter-arrival time distribution, that is pi naught. So, psi naught is equal to integration 0 to infinity e power minus theta times t d of at, where at is the CDF of inter-arrival time distribution with the real of theta has to be greater than 0. Now we are finding the probability generating function for pj's, that is a distribution of xn. So that is beta of z, that is a summation j is equal to 0 to infinity pj z power j. That you can write down in terms of Laplace transform. So this is a Laplace-Steelges transform. So Laplace-Steelges transform of a of t. So it's a psi of mu minus mu times z. Now we can find out the expectation of z, that is nothing but the beta dash of 1. If you differentiate a probability generating function, then substitute z is equal to 1 will be the mean number of arrivals, that is z. Mean number of inter-arrival time. So that is nothing but the mu by lambda. Now we can define the traffic intensity, that is nothing but rho. Rho is equal to arrival rate divided by the service rate. From above you can get rho is nothing but lambda by mu. It can be shown that the DTMZ is a positive recurrent when rho is less than 1. We have already made it is irreducible and aperiodic. Now we are giving the condition for a positive recurrent. When rho is less than 1, the given DTMZ is a positive recurrent. If rho equal to 1, it is a null recurrent. If rho is greater than 1, then it will be a transient. That means when rho is less than 1, all the states are positive recurrent. Therefore, the DTMZ is said to be a positive recurrent. Similarly, when rho is 1, all the states are null recurrent. Therefore, the DTMZ will be a null recurrent. And similarly, for rho is greater than 1. So, our interest is to find out the limiting distribution. So, when rho is less than 1, the DTMZ is irreducible, aperiodic and positive recurrent. Along with the condition B0 is greater than 0 and B0 plus B1 is less than 1. With this condition it is irreducible. With rho is less than 1, it is a positive recurrent. We can easily verify it is a aperiodic. Hence, the limiting distribution exists and it is unique. And that will be independent of an initial state I. Therefore, pi j will be a limit n tends to infinity, the probability of I to j in n steps. So, define the limiting distribution probability vector as a pi, which consists of pi naught, pi 1, pi 2 and so on, where pi j's are defined in this form, limit n tends to infinity p of I to j in n steps. We determine the limiting distribution by solving pi is equal to pi p and the summation of pi i's is equal to 1. So, the first one is a homogeneous equation. Including this normalizing condition, you will have a system of non-homogeneous equation. Solve this system of non-homogeneous equation to get the limiting probabilities. We get the limiting probabilities are 1 minus psi power j, where psi is the unique root of the equation. Z is equal to the Laplace-Steelges transform of the inter-arrival distribution with the variable mu minus mu z in the interval 0 to 1. That means first we have to solve the equation z is equal to psi of mu minus mu z, and you know what is the psi of mu minus mu z from the beta z. Solve the equation in the interval 0 to 1. So the unique root you have to substitute as a psi, then substitute psi in the pi j, and that will be the, since the unique root is in the interval 0 to 1, therefore the pi j 1 minus psi power j, that will form a probability mass function for the limiting distribution. Note that the Q length distribution found just before a arriving customer is geometric distribution with the parameter psi. The limiting distribution which we got it, that is just before a arriving customer. The Q length distribution found just before an arriving customer, which is a geometric distribution with the parameter psi. The best computational method for determination of the limiting distribution seems to be the direct matrix multiplication to get p power n for increasing values of n until the rows can be considered to be reasonable identical. Whenever for a larger n, p power n has the identical rows, it means that the limiting distribution exists. Therefore, the best computational method is find the p power n for a larger n until the rows can be considered to be a reasonably identical. It is important to note that the embedded Markov chain analysis gives the properties of the number in the system at arrival epochs. The q of t for t greater than or equal to 0, that is a discrete state continuous time stochastic process, whereas a qn for n is equal to 0, 1, 2 and so on, that is a embedded time homogeneous discrete time Markov chain, and that is qn is nothing but q of tn minus 0, that is nothing but number of customers in the system just before the nth arrival. Hence, it is important to note that the embedded Markov chain analysis gives the properties of the number in the system at arrival epochs, not the departure epochs or not at the arbitrary time instance. It gives the embedded Markov chain analysis gives the properties of the number in the system at only at the arrival epochs. As pointed out under the discussion of MG1Q, the limiting distribution of the number of customers in the system at arrival epochs, at departure epochs and at arbitrary points in time are the same only when the arrivals occurs as the Poisson process. So, in the MG1Q, the limiting distribution of the number of customers in the system at arrival epochs, departure epochs and the arbitrary time points are same because the arrival occurs in the Poisson process or inter-arrival follows independent exponential distribution with the same parameter, whereas in the GIM1Q model, the embedded Markov chain results gives the limiting distribution of the number of customers in the system at the arrival epochs only. That is not same as the limiting distribution at the departure epochs, and that is also not same as the arbitrary time points. Now we are going to discuss the limiting distribution at the arrival at the arbitrary time points. Prabhu and Bhatt derived the results of a limiting distribution at a arbitrary time t. Let Pj is the probability that limit t tends to infinity, the probability Qt is equal to j. So this is nothing to do with the embedded Markov chain Qn. We are finding limit t tends to infinity, probability that Qt is equal to j, where Qt is the number of customers in the system at arbitrary time t. The limiting distribution exists whenever the row is less than 1, and the probability that no customer in the system in a long run, or the limiting in a long run, that P naught is equal to 1 minus rho, and the Pj is equal to rho times 1 minus psi power j minus 1 for j is equal to 1, 2 and so on. So this is the limiting distribution at arbitrary time. To determine the distribution of waiting time of a customer, we need a distribution of a number of customers in the system at the time of that customer's arrival, if you want to find out the distribution of waiting time. Replace rho by psi in the MM1 results, since the Q length distribution is same. Our interest is to find out the waiting time distribution, since the limiting time distribution at arrival epochs is the same as the limiting distribution of a MM1Q model. Therefore, you can replace this rho in the MM1 results by psi to get the Q length distribution, to get the waiting time distribution. Therefore, by replacing rho by psi in the MM1 results of waiting time distribution, you get the waiting time distribution for GIM1Q as the CDF of waiting time distribution is 1 minus psi times e power minus mu times 1 minus psi times t for t greater than or equal to 0. For t is less than 0, it will be 0. So this is the waiting time distribution for GIM1 queuing system. First we found the limiting distribution at the arrival epochs. Next we find the limiting distribution. Next we discuss the limiting distribution at the arbitrary time points from the Prabhu and Butt results. Then we have discussed the waiting time distribution. Now we are discussing the moments of queue size. The mean and variance of waiting time, time spent distribution, and its mean and variance can be obtained. Once we know the limiting distribution at the arrival epochs, as well as you know the waiting time distribution, you can find the mean and variance of waiting time. By adding mean, you can find the mean of time spent also. You cannot use the mean value approach because the arrivals are not Poisson process. So you can find out the average time spent in the system, that is E of t, will be average number of customers seen by at the arrival epochs, that is ELA, multiplied by 1 by mu, plus the average service time, that is 1 by mu, will give the average time spent in the system. Since the arrivals are not Poisson processes, we cannot use the mean value approach. By simplification, you can get, already we know what is the average, what is the distribution of number of customers seen at the arbitrary, already we know the limiting distribution at the arrival epochs. So we can find the mean from those results, then multiply by 1 by mu plus 1 by mu will give the average time spent in the system. Then you can find the variance of time spent in the system also. The first, this one, the mean and variance of waiting time. Since you know the waiting time distribution, you can find the mean and variance. Suppose the inter-arrival time is constant. Then the Laplace-Steelges transform will be e power minus theta. You can find the limiting distribution for the DM1 model also. When the inter-arrival time is a constant, then the corresponding queuing model is denoted by DM1Q. So we can find the limiting distribution at the arrival epochs as 1 minus psi power j, where psi is the root of the equation, psi is equal to e power minus mu times 1 minus z, because psi of theta is equal to e power minus theta. So to get the root of the equation, you have to solve z is equal to psi of mu minus mu z. You have to get the root of the equation, z is equal to psi of mu minus mu z. So in the DM1 model, psi of theta is equal to e power minus theta, therefore it will be z is equal to e power minus mu times 1 minus z. So if you solve this equation, you will get psi, that is a unique root between the interval 0 to 1. Substitute psi here, so that is the limiting distribution at the arrival epochs of DM1 queuing model. Now we move into the multi-server queues. The embedded Markov chain analysis of the queue GIM1 can be easily extended to the multi-server queue GIMC, where C is the number of servers in the system. Since the number of servers are greater than or equal to 1, the one-step transition probability matrix will be different now. That means each element Pij will be different from the GIM1 corresponding one-step transition probabilities Pijs. So here we can consider three cases for the initial value I and the final value j. So corresponding to the each cases, your Pij can be obtained. For the case 1, I plus 1 is greater than or equal to j, greater than or equal to c, you will get Pij in this form. This represents I plus 1 minus j service completions during a inter-arrival period when all C servers are busy. So the case 1 is related to all C servers are busy, means the number of customers in the system is greater than or equal to C. That is a situation in which you are getting the one-step transition probability for the embedded Markov chain. For the case 2, the I plus 1 is less than or equal to C, whereas j is less than or equal to c also. This case is related to I plus 1 minus j out of I plus 1 customers complete the service. The third case is related to I plus 1 is greater than c as well as j is less than c. This represents I plus 1 minus c customers complete service with the rate c mu. Then C minus J out of C customers complete the service. To get the complete limiting distribution at the arrival epochs, you can refer Gross and Harris to get the complete result. So here we have discussed only the one-step transition probabilities, how that is different from one-step transition probabilities of GAM1 model. Now we move into GAM1N queue. So this queue is similar to GM1, but now the system capacity is restricted to some finite number capital N. Therefore, the relations between Qn and the Qn plus 1 will be a smaller change in it. That is, a Qn plus 1 will be minimum of Qn plus 1 minus Xn plus 1 comma n, where Xn plus 1 is the number of potential service completion during the inter-arrival time period. So once you know Qn plus 1 in terms of Qn, we can conclude, since Qn plus 1 is in terms of only Qn and Qn plus 1 is independent of Xn plus 1, therefore Qn form a time homogeneous discrete time Markov chain, and one can find the one-step transition probability matrix P with the entities Pij's. Here also you can verify the row sum will be 1. And each Bi is nothing but the probability mass function of each Bi's are nothing but the distribution of X. Once you know the one-step transition probability matrix, we can go for finding the limiting probabilities. Note that the last two rows of the matrix P are identical because of the Markov chain effectively starts off with the n customers from either of the states n minus 1 and n. Therefore, if you see the last two rows of the transition probability matrix, both the rows will be identical because of the Markov chain effectively starts off with the n customers from either of the states n minus 1 and n. Since the finite state DTMC is irreducible, aperiodic and positive recurrent, then the limiting distribution exists. So let pi be the limiting probabilities defined as pi j is equal to limit n tends to infinity Pij of n. We can determine the limiting distribution by solving pi is equal to pi p and the summation of pi a is equal to 1. Here there is no restriction on rho because it is a finite state Markov chain. At the end, we move into GI-G1 In this queuing model, a single server queue with the arbitrary arrival process, that means the inter-arrival time or non-exponential distribution, and arbitrary service time distribution, that means the service time is also non-exponential distribution, with the infinite buffer. Let S be the random variable representing the service time, and the expectation of S will be 1 by mu, where mu denotes the service rate. Let lambda be the mean arrival rate. Assume that lambda is less than mu so that the queue is stable. For a stable system, you need lambda is less than mu, where lambda is related to the mean arrival rate and mu is related to the service rate. One can show that for a stable GI G1Q, the utilization is given by lambda by mu. Utilization is nothing but what is the probability that the server is busy. So that is given by lambda by mu. We are interested in the distribution of number of customers in the system, in the limiting distribution. We are interested in the limiting distribution of a number of customers in the system. Let Pn be the probability that there are n customers in the system in a long run. The probability that the system empty is given by P0, that is nothing but 1 minus utilization. The utilization is given by lambda by mu, that is the probability that the server is busy in a long run. Therefore, the probability that the system is empty in a longer run is same as 1 minus utilization, that is 1 minus lambda by mu. Note that Little's formula can be applied to obtain the average measures such as mean system size, mean queue size and mean delay. Since it is a stable system with the lambda is less than mu, you have the probabilities, and once you know the limiting distribution, you can use the Little's formula to find out the all other average measures. That means using the limiting distribution, you can find out the average number of customers in the system in a long run. Once you know the average number of customers in the long run, with the mean arrival rate lambda, you can find the average time spent in the system. Once you know the average time spent in the system, you can find the average time spent in the queue also. And once you know the average time spent in the queue, using the Little's formula, you can find the average queue size also. So, using Little's formula, with the help of a limiting distribution, we can find the average number of customers in the system, then average time spent in the system, average delay and average queue size also. So, in this lecture, we have covered the non-Markovian queues, namely GIM1, GIM1N, GIMC, GIG1 queues. With these 5 lectures, the renewal process is over. Here is the reference of renewal processes.